Hi, I'm Devin. I lead the Developer Security Tools group at Apple. And as Tanya mentioned, I'm going to tell you about our work on eliminating entire classes of memory safety vulnerabilities in C-based languages. These days, we all have personal computing devices. In our living rooms and offices, our cars and bedrooms, we often carry them around in our pockets everywhere we go. These are essential tools that we trust with the mundane, but often intimate private details of our lives. Our location, our photos, our messages, our contacts, our browsing history, and more. At the same time, these devices are connected to the internet and to each other. And so security vulnerabilities in them open us up to attacks from bad actors. The cost of attacks on individuals can range from identity theft and money, to blackmail, to threats on the lives of journalists and human rights activists. And memory safety is at the forefront of these security challenges. There is a large amount of security-sensitive code out in the world written in memory-unsafe languages. Our memory safety strategy is that we believe that full memory safety requires using a memory-safe language. At Apple, that's Swift. However, there's simply too much code in C and C++ and Objective-C to rewrite it all. And so we have taken to adopting memory-safe languages in new code and rewriting high-value code bases in memory-safe languages. This is a great strategy, but it does come with some challenges. And the metaphor that we use here is islands of memory safety. We have these islands of memory safe code. These are the green islands in this vast ocean of blue memory unsafe C and C++. And as much as we are growing the islands as quickly as we can, we need to do something to protect that large ocean. Now, we strongly believe that we cannot make C and C++ fully memory safe. That's just not possible without changing the language so much that we would have to rewrite all the code anyway. And if we're going to rewrite the code, we might as well rewrite it in a more modern language. But we can aim to eliminate entire classes of vulnerabilities. And if we can't eliminate them, we should try to mitigate them extremely strongly to make sure that attackers can't take advantage of them. Now, I want to compare this to static and dynamic bug finding, which are incredibly useful, but they're not comprehensive. They don't satisfy the goal of eliminating entire classes of vulnerabilities. The best they can do is find as many bugs as possible before they get into the hands of our users. So they're great, but they're not enough. I want to highlight what we view as our definition of success, because it's very ambitious. Our goal here, fundamentally, is about shifting attacker behavior. We want to drastically increase the cost of attack development so that attackers move on either to other vulnerability classes or to unprotected code bases. And what's the ultimate sign of success? It will be when memory safety bugs are no longer the low-hanging fruit for attackers. When attackers move on to logic bugs, we know we will have done a good job with memory safety. When I say memory safety, what do I mean? We tend to think of it as having 5 different dimensions: guaranteed initialization, bound safety, lifetime safety, type safety, by which I really mean cache safety, and thread safety. And in the rest of this talk, I'm going to tell you about each of these kinds of memory safety, the work that we have done to try to eliminate security vulnerabilities in that space, and also where we think that there's additional work that needs to happen. Let's start with guaranteed initialization. This is the property that all memory is initialized before it's read. We developed the ftrivial autovar init extension in Clang to protect stack memory. This guarantees initialization to 0, and it prevents information disclosure attacks and many stack grooming attacks. We can also zero initialize on free to protect the heap. This is an approach that we have deployed on hundreds of millions of lines of code. It's been very successful. At the same time, it's not perfect. And one thing I do want to point out is that 0 is not the programmer's intended value all the time. And in our studies, it's roughly around 20% of the time, zero initialization is not the correct value, so that represents a logic bug. Nonetheless, this has been very successful at preventing some of the worst security problems from use of uninitialized memory. So it's really quite good. For more information on zero initialization, you can see the RFC that we posted. This was 6 years ago now. I can't believe it's been that long on the LLVM forums. Now let's move on to bound safety. Bound safety is about making sure that when the programmer is accessing a region of memory, that they're only accessing within that region and not outside of it. I'm going to tell you about two different bound safety approaches that we have taken, one for C and one for C++. Let's start with C. We developed the fbounds-safety language extension for the C language. In this extension, users specify for buffers and bounds a relationship between the two of them with code annotations. The idea is that these annotations are enough so that the compiler can insert runtime's bounds checks to trap on out-of-bounds memory accesses. Now, this is not pure static analysis. It's not trying to prove that everything is in bounds at compile time statically. Rather, what the compiler does is ensure that there is enough information at compile time so that it can generate the appropriate checks at runtime. With this language extension, we made a number of key design choices to lower the adoption cost, such that the time to adopt this language extension is roughly around 1 hour per 2,000 lines of code. This is something that we have adopted on millions of lines of code at Apple, including hundreds of thousands of lines of XNU, the kernel in our operating systems. So let me tell you more a bit about it. Here we have a simple C function that takes in a buffer and a count and fills in that buffer. And those of you looking might notice that it does have an off by 1 overflow. How can the programmer make this code bound safe? Well, they will make a code modification to tell the compiler that count, the second parameter, has the same number of elements, that the buffer has in it. So this is establishing a relationship between the buffer parameter and the count parameter. This is enough for the compiler to add a runtime's bound check to make sure that this access is in bounds. And this then, when the code runs, will safely trap when it goes past the end of the buffer rather than right past the end of the buffer. Now, what's great about this approach is that this use of annotations allows the language extension to preserve the binary interface and signature of the function. This is a type attribute that doesn't change the type of the function or of the parameter, and this allows for incremental adoption. Programmer can adopt this on one part of their code base and not on another, and the two things can still fit together without causing problems. As we'll see, this is a really important property for many of the safety protections that we have developed. Incremental adoption, so that it's not all or nothing, so that it can happen slowly over time, is a very important property. Now, this does have an annotation burden, and so we also developed as part of this, a technique that tries to reduce that. For this, we use implicit wide pointers for local variables. These wide pointers, or fat pointers, carry their bounds. So for example, here we have a function with a local variable. The compiler will implicitly transform that underneath the hood to have that local variable be a wide pointer that contains both the pointer and the bounds of it. What this means is that the programmer only needs to annotate the bounds on their ABI surface. ultimately requiring fewer code changes and requiring less work to adopt. So what we've done is combined lightweight annotations on the ABI surface with implicit wide pointers everywhere to give us this incrementally adoptable bound safety with a reasonable annotation burden. And it's been very successful for us. There's more information in the Clang RFC that we put up. My colleague Yul Na gave the EuroLLVM 2023 keynote on this approach. And my colleagues Henrik and Patrick gave a tutorial yesterday on this. I encourage you to take a look at that tutorial when it's up on YouTube, if you didn't get a chance to watch it. We have a full implementation up in Swift's fork of LLVM, and this is something that we are in the process of upstreaming to llvm.org. It's something we're really excited about, and something that we're looking to have wide use throughout the community. Now let's move on to C++. C++ is a different language than C. It's a much richer language. It has a richer library ecosystem. It has much more language affordances. And so we took a different approach for bound safety in C++. We built the Wunsafe-buffer-usage compiler warning, and we built the hardened libc++ library. And we call the combination of those two things the C++ safe buffers programming model. And this guarantees bound safety for C++. In this approach, the compiler rejects raw pointer arithmetic. If you have C++ code with this warning on, it will warn on it, and most of our users turn this warning into an error and say, nope, I'm just not going to use any raw pointer arithmetic. Instead, the programmer uses bounds-checked standard library extractions. It's like std_span and std_vector. This is something that has been adopted on tens of millions of lines of code. And in terms of adoption speed, we find it's very bimodal. There's a lot of C++ code out there that I call C written in C++. And for that, we find that the adoption cost is roughly 2 times higher than for the C fbounds-safety. So that's around 1,000 lines of code per hour. But for modern C++ code bases that use a bunch of these library abstractions already, rather than raw pointers and malloc, it is extraordinarily fast. A quotation from one of our adopters said that they were zooming. It's really impressive to see how fast a modern C++ code base can adopt this technology and get bound safety. So let's take a look at how this works. Here's our old friend, the same function from before that fills an array, fills in a buffer. Here, in order to make it bound safe, the programmer will turn on the warning that rejects raw pointer arithmetic. They'll get an error saying, look, programmer, you're doing this array access on a raw buffer. That's just a pointer arithmetic under the hood. You said you don't want that, so we're going to complain to you. Then the programmer will change the type of the buffer to be a span, to indicate that it's a contiguous span of integers. Then underneath the hood, through the use of hardened libc++, the span implementation checks the bounds of that array indexing operation via operator overloading. And this is an example of why we chose a different approach for C versus C++. In C++, we have things like operator overloading and a very rich standard library where we can rely on those parts of the language rather than needing to have a full-blown language extension. We have more information on this in the Clang RFC, and we also gave LLVM 2023 talks, both on hardened libc++ and on the unsafe buffer usage warning. And the implementation for this is in llvm.org open source. Now let's move on to lifetime safety. This is a trickier problem. I'm again going to describe 2 different techniques that we have taken. I'll start with one that is based on static analysis. Over the last several years, we have developed in the Clang static analyzer a set of checkers that enforce a strict programming model around reference-counted smart pointers. Now, I want to emphasize that this is not bug finding like you might be used to in the Clang static analyzer. Instead, it is trying to enforce this programming model such that if the programmer sticks to that model, then they have a guarantee that they won't have this class of bugs. This is also something that we have adopted on millions of lines of code, and it's been quite successful. So how does this work? Here's an example of some potentially buggy code. The programmer has some container. That container has a smart pointer field in it with a resource, and they're getting that resource as a raw pointer from the smart pointer. Then they're calling some other function or method that really could do anything. The programmer has no idea what it could do. And in particular, that could overwrite that resource. And if it happened to be the case that that smart pointer in the container was the last thing that was keeping the resource alive, it could be freed. And then this use after that is a use after free. So with this static analysis, the compiler gets an error saying, look, you're using this resource, you've put it on the stack, you're using this resource, and in between, you're doing something where you can't guarantee that the resource won't be released. That's a problem, you need to fix it. How does the programmer fix this? They change the type of resource to indicate that its lifetime must last for the entire scope. In this case, with a ref pointer, smart pointer class, where the runtime implementation guarantees the lifetime of that underlying resource until the destructor is called. This implementation is in LLVM.org. We have used it on WebKit smart pointers, but we think it's generalizable to all sorts of other reference-counted shared pointer disciplines, and that's something we'd be excited to talking to folks about to see if you think it could work for your code bases. Now, what about situations where there's not a reference counting discipline? What if the programmer is using raw malloc? What if it's C? In this case, we need to take a different approach. Here we have developed a language extension for both C and C++ that mitigates use after free vulnerabilities by limiting data pointer type confusion. So this doesn't eliminate the use after frees, but it does mean that when there is a use after free, it makes it much, much harder for the attacker to take advantage of it. This is an approach that we have deployed on hundreds of millions of lines of user space code. We've also taken a similar approach in the XNU kernel. And this is really exciting. So how does the compiler part of this work? Well, I'll give an example of C, and then we can talk about C++. This whole approach is driven by a new typed memory allocation attribute that library vendors who surface allocation APIs can place on their allocating functions. So here there's this new attribute that we have developed, and it says two things. One, this is an allocating function, and the size of the allocation is passed in the first parameter. And two, the library vendor is also going to vend another allocation entry point, malloc typed, that contains a second parameter that includes extra information for type information. And the allocator will use this type information to try to isolate the allocation in a way that improves security. So now library vendors vend two for each entry point, like malloc or calloc. They vend an additional entry point that contains the extra type information. Then, when the compiler sees a call to the standard allocation function, it will transparently rewrite that during compilation into a call to the typed pair of it. In this case, malloc typed. And it will look and try to infer the type of the thing that's being allocated, in this case, the type of struct some type, and pass in a type descriptor to the allocator, which the allocator is then free to use however it chooses. We need similar support for C++, but again, C++ is a much richer language, and so we can use something that fits in with C++ and some of the existing language affordances that it has. We have a proposal P2719 which extends the language so that programmers can provide a templatized operator new and delete. And this proposal changes the lookup rules so that if there is a templatized operator new or delete, the compiler will prefer that before looking to find normal operator news and deletes. And since it's templatized, then the implementation of that can use the template parameter however it sees fit in order to pass the type information to the allocator. We have a Clang RFC up for this. My colleague Oliver Hunt also gave a talk about this at LLVM 2024. And this is something that we're working with the C++ Standards Committee to standardize, and I expect this to be part of C++ 26. We're very close to getting it approved. This is also in the process of being upstreamed. The C++ support was merged last week, in fact. Now let's talk about type safety. And here again, what I mean by type safety is casts. And we don't, in my opinion, have as good answers here, although we have some. We have developed another static analysis enforced programming model, again, that works with the WebKit's APIs, that rejects unchecked casts unless the compiler can prove that they're safe. This works great for C++ code bases with a runtime representation of types. So I think this would work quite well in the LLVM code base. There's lots of other code bases that do that, especially if the code bases have an idiom of always using runtime checked casts for downcasts. However, I don't think that we have a viable approach for C code bases, nor for C++ code bases that don't have some notion of runtime type information to rely on for checked casts. And so this is an area where I think that we as a community need to do more investigation in order to figure something out. For more information on the static analysis that we've applied to WebKit, we have that in upstream in llvm.org. Now let's talk about thread safety, and this is the scary one. We really don't have strong ideas for how to handle thread safety. We know that it's going to be very important. In many situations, thread safety can lead to use after free bugs, it can lead to leaks, and this is something that attackers absolutely can take advantage of. And this is an area that needs much more investigation. Clang has the W thread safety warning, which is quite useful, but it doesn't eliminate the entire class of thread safety data race bugs. And so our general recommendation is for thread safety, if you want it, you need to use a thread safe language. For example, Swift Concurrency's actor model provides data race freedom. But I do think that there's more that we can do here for C and C++. I'm just not sure what it is. And so I would love to hear from all of you if you have ideas on this front, because I think this is going to be increasingly important. As we plug holes in bound safety and lifetime safety, attackers will shift to focus more and more on thread safety, and it will become increasingly important. Now, I want to take a little bit of a detour here and talk about memory safety in heterogeneous code bases. So let's go back to our metaphor around islands of memory safety. We are increasingly in a world where our code bases are a mix of code written in a memory safe language and now perhaps partially safe C and C++. And what we want it to be the case is that if we have adopted a bunch of these memory safety technologies on C and C++, that when C and C++ interact with a memory safe language and interoperate with them, we want to have that interoperation be safe and to preserve the partial memory safety that we have worked so hard to provide in C. So to use this metaphor, we need to protect the beaches. It's not just enough to build out the green islands and to partially protect the oceans. We need to do something pretty strong on the beaches as well. At Apple, we use a mix of memory safety technologies, and it's common that code bases will contain all of these. We have Swift that's fully memory safe by design. We have this bound safety extension that adds bound safety to C with annotations. We have hardened C++, which is bound safe via the libc++ library and the compiler mode that rejects raw pointer arithmetic. So what we really need to do in order to secure the boundaries is think about how do these things interoperate with each other, and what can we do to make sure that the guarantees aren't dropped there. This is something we've done a lot of work on over the last year. So for example, we can import types annotated with bound-safety annotations from C into Swift as Swift's span type. Similarly, when Swift calls into C++, we can take advantage of lifetime annotations in order to make that more safe. And if you haven't seen it, I encourage you to see my colleague Gabor's talk from yesterday on C++ interoperability with memory-safe languages. It describes a number of the annotations that we've developed in order to make this interface more secure. And then, of course, we also need to protect the interface between C, that's bound safe, and hardened C++. And this is something that we've done some investigations on making this safe with strict compiler warnings. So we can't forget, we put a lot of effort into developing each of these individually. We can't forget how these things need to talk to each other. So let's go back to memory safety. We talked about guaranteed initialization. For that, we developed ftrivial autovar init with 0 initialization. For bound safety, we developed approaches for both C and C++. For lifetime safety, we use a typed allocator with compiler support, and we've developed static analysis for C++ code bases that use a fairly disciplined discipline. For cache safety, there's a little bit that we can do there, but really there needs to be more investigation, especially for C. And for thread safety, we don't have strong ideas there, and so we'd love to hear more from the community. I want to step back here now and synthesize some of the ideas that we've talked about, because underlying a bunch of these approaches is a recipe that we've developed, and that recipe is to enforce what I call strict programming models. What are the ingredients of a programming model? Well, we commonly see that there's 3 things that we need to do in order to eliminate entire classes of vulnerabilities. 1, we develop compiler checkable local rules. 2, we need the developer to provide annotations to inform the compiler about things that they know but that the compiler doesn't. And 3, we often find we need some level of runtime support. So let me talk about each of these in turn to provide a little bit more detail. Ingredient 1 is compiler checkable local rules. Typically, these rules restrict the programmer to a subset of the language. And by restricting the programmer to that subset, the programming model can make strong guarantees. And we should think about this more like a programming language feature rather than bug finding. Sometimes we implement this in the compiler, sometimes it's implemented in a static analysis, but we should think of it like a programming language feature. And when programmers think about this that way, we find that it's much more successful to have it be adopted. And the reason for that is that they're willing to adopt a new language feature to get strong guarantees. Now, it's typically very important that these rules be easy to reason about locally for a programmer. And it should be easy for the programmer to tell, does this particular piece of code follow the rules or not? And then if it's easy for a programmer to reason about, then it should also be easy for tools to reason about, so that the tools can ensure that the programmer doesn't make mistakes. So the second component is developer-provided annotations. It's often the case that for these programming models, the compiler needs some amount of more information that it doesn't know, but the developer typically does. These are often key invariants that the programmer has in their head and expects to hold. They might not hold, but the programmer expects it. And this enables the compiler to reason about the program. This affords what we call modular reasoning, or assume guarantee style in PL jargon, locally, for example, on a per function basis. This is analogous to type checking, where, for example, if the compiler can guarantee that the caller passes a string as the first argument, the callee can assume that that first parameter is a string as well. So this kind of guarantee things at the caller so the callee can assume it is very powerful as a mechanism for these programming models. and we often need the programmer to provide these annotations to inform the compiler of the invariants. And then finally, we found that we do often need some amount of runtime support. Compile time checks are just not enough. The reason for this is that tools often can't reason precisely about program behavior. As we all know, that's typically undecidable. And a lot of times, in order to have safety, we need to establish, track, and check global invariants. And this is something that's just very difficult to do purely statically. It's expensive, it does not scale to large programs. And so when we're faced with a problem like this, we typically design a runtime abstraction to handle the difficult cases. And the runtime abstraction can do some amount of checking at runtime, and then locally we can guarantee that the right runtime abstractions are used at compile time. So this is ultimately an escape hatch for global reasoning. So I'd like to talk through how a couple of the approaches that I outlined fit this recipe. Let's talk first about the bound safety extension for C. We have a local rule. The programmer must only dereference pointers with known bounds. The developer provides annotations in the form of bounds attributes. And there is runtime support. The compiler is code-genning in traps that dereference if a pointer is out of bounds at dereference time. For our C++ approach, it's somewhat similar. The local rule is no raw pointer arithmetic at all. The developer needs to provide annotations here in the form of adopting the span utility class for buffers. This tells the compiler what's a buffer and what the programmer expects to be able to use operations that syntactically look like pointer arithmetic. And of course, there's runtime support in the hardened standard library inside the implementation of span for the bounds checks themselves. For the WebKit smart pointer analysis, the local rule is thou shalt not have raw pointers on the stack across unknown calls. And the developer provides annotations here in the form of ref pointer utility class adoption for those pointers that need to be on the stack. And again, the runtime support is in the ref pointer implementation itself, which handles the bookkeeping to keep the raw pointer alive. So this is a pretty general recipe. And one challenge that I have for the community is to think about if there's other security problems out there that you are all facing that we think we can apply this kind of recipe to. My hunch is that there's a whole lot more that we can do here, and this can perhaps inspire a lot of different approaches to eliminate entire classes of security vulnerabilities. So if you have ideas here, I'd love to talk to you at the rest of the conference today and learn about the use cases that you have or the problems that you're facing from a security perspective. I do want to talk about the costs of these strict programming models. And we find that the biggest limiting factor in adopting them is the programmer effort. So for example, if we look at zero initialization or the typed allocator, that required relatively little work on the part of adopters. And so it was easy, it was actually a lot of work, but like in the scheme of things, it was easy to roll out to hundreds of millions of lines of code. Whereas if we look at our bound safety approaches, these are very powerful, but they do require more adoption work on the part of the programmer. And so our adoption so far is in the millions and tens of millions of lines of code, rather than the hundreds of millions of lines of code. And what I think this really points to is for some of these programming models, for them to have widespread adoption across industry, we really must invest in tooling to lower the adoption cost. This is something I think that we as a community need to work on. And ultimately what we need to do here is build annotation inference tooling. The main bottleneck is having the programmers actually write down their annotations that express their invariants. And the problem here around building these tooling is that even though the annotations can be checked locally, and we typically design them to be that way, they often must be inferred globally. So for example, what annotation is inappropriate in a callee might depend on the caller and what happens there, or vice versa. So this essentially requires whole program reasoning. So one proposal that I have for how we can extend LLVM in Clang with infrastructure to make this possible is summary-based inference tooling. And if you're familiar with the idea of thin LTO, this is a very similar idea, but applied to the front end, where we can, in the compiler, achieve whole program reasoning with summaries. So when the compiler compiles each file, it can also emit a per file summary of the interesting things that each function does from a security perspective, from a memory safety perspective. Then have a phase of the build that merges those summaries, iterates on them to a fixed point to infer annotations, and then apply those summaries or apply those annotations automatically to each file. This is a very powerful approach for analysis, and it's something that I think that we as a community should start working to build together. And I will be working with folks both at Apple and at other companies to put together an RFC for this in the coming months. This kind of infrastructure would also be broadly applicable. We could use it for the Clang static analyzer to enable cross-translation unit analysis to scale across larger code bases and with a lower maintenance cost. It would also reduce false positives and false negatives. It's also extremely useful for this problem of safe interoperation with memory-safe languages like Swift and C++. Again, safe interoperation there typically requires the programmer to add annotations on the C and C++ code so that Swift or Rust can know what promises that C and C++ code makes, so it can know how to import that safely and ergonomically into the memory-safe language. And so we can use these same mechanisms and this same infrastructure to infer things like lifetime annotations and escapability annotations for use in interoperation with memory-safe languages. So this is something I'm very excited about, and I'd love, if you're interested in working on this kind of thing, I'd love to talk with you later on today. So that's the end of the talk. I do want to summarize it a little bit. Memory safety is a really important problem for our community. And I strongly believe that memory safety really only comes with full memory safe languages like Swift, like Rust. However, we have all of this existing C and C++ code, and so we need to do as much as we can to protect it. We also need to make sure that we have safe ergonomic interoperation with our existing C and C++ code and the new code written in safe languages. One of the best ways to do this is with strict programming models. These provide a recipe for eliminating entire classes of memory safety bugs in C and C++. Again, it won't make the languages completely memory safe, but it can mean that attackers will have to find completely different kinds of bugs to take advantage of. There's 3 components to a typical programming model: a set of local rules, developer-provided annotations, and runtime support. And the annotation cost from the developer is, in our experience, the major limiting factor in adoption. So we should, as a community, absolutely invest in automatic inference tooling. Thank you.
You mentioned that zero initialization is not always the right thing. Did you also consider making initialization compulsory in the language?
Yes, and that is, I think, something that is very reasonable to do. That does have a higher adoption cost, but I think there are lots of code bases where that's a very reasonable thing to do. You need to be a little bit careful with that because there are some patterns that programmers use where they rely on flow-sensitive compiler warnings to tell them when they haven't initialized something to find bugs in their logic. And so if we forced those code bases to initialize something like syntactically, then that can cause them to introduce logic bugs. But I think in general, those code bases are rare. In general, that doesn't happen very much. So I think that's a great thing. And enforcing that, if you can enforce that in a particular code base, that is a great place to start.
Yeah. So you could also make that a standard option to use rather than the zero initialization option.
Absolutely.
Okay. Thank you.
Yeah.
Hey, so that's very loud. First of all, thanks for all the work, and also thanks for upstreaming all of this. I know it's not, the default course that everything gets upstreamed, so thanks for that. So my question is, so there's this saying that says security research is measured by how much slower you make everything. So I was wondering, one reason why people don't adapt security measures is because the code gets slower. Even like, for example, you use C++, you use shared pointers, suddenly you have terrible code gen. What do you think about essentially treating situations where the safe code is slower than the unsafe code because of hardening checks, whatever, that don't get optimized out? What do you think about treating this as an actual part of this effort to make code more secure?
And I think in many cases we have done that. So for example, for the bound safety extensions, Florian Hahn developed the new constraint elimination pass that was specifically in order to eliminate redundant bounds checks for fbounds-safety, for example. So we have done a lot of work in the optimizer in order to reduce the costs of these things, and that's very important. Typically, these approaches do come with a cost, and it can vary depending on the approach. We put a lot of effort into reducing the cost of them, improving the compiler, improving the optimizer to reduce the cost of them. And then sometimes we do also try to find other ways to pay for these costs when we deploy them by optimizing other parts of the system, for example. Performance is extremely important. At the same time, we do need to acknowledge that the entire community is needing to do a huge amount of work in order to pay for our lack of memory safety. And so we can't say that performance is the most important thing. We need to balance performance and security.
Thank you.
Okay. How do you, in C++, it's common pattern not to use pointers, but say pass pairs of iterators to a function. How do you deal with that, and how do you deal with the ABI implications? For example, like when you probably need to roll out an ABI incompatible version of libc++ into your system.
Yeah, so that's a really great question and a great point. And in some cases, so for example, std_span itself, we do not need to change the ABI of that to provide bound safety. But for std_span iterator, which in a lot of the existing ABIs is only a single pointer that cannot be bound safe. And so we have in libc++, Louis Dion has developed extensions for libc++ that enable libc++ library vendors in different environments to specify what ABI they would like to use for their iterators. And in particular, for say a span iterator, a library vendor can say, I would like iterators for std_span to be 3 words and to contain both the pointer and an upper bound and a lower bound. And then in some cases where we can't change ABI or where the use of iterators can introduce other bound safety problems, as part of Wunsafe-buffer-usage, we warn on those idioms to say, programmer, you shouldn't do that.
How does it compare to libc++ debug mode?
It is inspired by that, and it's kind of that debug mode was kind of the foundation of our thinking about that. The checks that we use for hardened libc++ are a subset of the debug mode checks, but we have gone through the effort of making sure that rather than just being a debugging feature, that they are a programmer visible feature, something that we are moving to standardize and has been accepted for standardization in the C++ language. So it's absolutely inspired by that work. In some cases, it depends, underneath the hood on that work. Although the things that we're using tend to be the faster debug checks. There's a bunch of awesome debug checks that are too slow to have on in production.
Thank you.
I was Oh, cool. I was wondering if you have any thoughts about how you benchmark or measure these approaches starting to have success. Like, do you see reduction in exploits, or are there other ways to measure this is successful?
Yeah, so that's a really great question and an important one. And we have kind of two metrics that we use to measure our own success. One is around adoption, and if we can talk about what fraction of particular security-sensitive code bases have adopted these technologies, that tells us something about success from an ergonomics perspective. How easy is it to adopt? Are programmers willing to adopt it? And that is a really important aspect of any of this kind of programming model work. But then ultimate success is around shifting attacker behavior. And so we measure success there twofold. One, we of course attack our own systems, we fuzz our own systems, and it's been the case, for example, that we have found some holes in our programming model by fuzzing against them and fixed them. And then we also look long-term at how attackers shift their behavior. Are they moving from attacking one subsystem to another subsystem? Are they moving from attacking one particular kind of bug to another kind of bug? And that is how we measure success in the long term. And that's fuzzier, that takes longer to measure, but it is something where ultimately that's what we need to do in order to convince ourselves that we have made a difference.
I don't know, question or comment on your SYN-LTO approach, right? So that calls for abandoning shared library, right? Because if you want to whole program, you need static libraries, right? And then you trade in one class of bugs, like, okay, this is bug in my code, and I could prevent it, but I will ship the bug with the library and no way to easy update it. Now, when the library fixed, I need to redistribute all the applications linked with this. What's your, how you look at this trade-off?
Yeah, and so one thing I do want to say is I don't think that there's incompatibility with this approach with shared libraries. For the annotations that we are inferring, they can typically be expressed as attributes in headers. And so what I'm imagining here is annotation inference. What it's doing is producing header annotations. That means that on the portions of the code that a particular code base controls, they can run this inference algorithm on the code that they have, put that in their headers. Then a library vendor who's vending a shared library can do the same thing and put in the headers these annotations. Now, of course, a library vendor might not, want to add their own annotations, or they might not have been able to do that yet. And for that, we can use a technology that's in Clang called API nodes that was designed for exactly this purpose. It allows a particular project to add annotations. Basically, the programmer provides a YAML file that provides annotations, Clang attributes in a YAML format and applies it to another project's headers as it's compiled. So this allows one project to add annotations to another project's headers without needing to modify those headers. So I think in both of those cases, we have approaches that can work here. Does that answer your question?
Kinda, yeah. Thank you.
Unfortunately, we are out of time, so please talk to Devin after the talk. We will now have a 30-minute break. Thank you.